in in cutting the field where you know as how will the stream how the stream will be going is that starting with of them. Yes, I'm back. How it will be done is that first of it you can frequency and you can put it in the classroom. And let's start with question one. Mm, I we already know answer. That's what we are talking about. Aid of the system. How to overcome regulation. Yes, we are talking about the schematic parameters. Now, who controls the generator, the frequency of this gas to control them? That's the schematic under when the basic principle that you can remember and then you can help you remember what that want to look at what is happening at the generator side. When we are measuring the frequency, we are simply measuring comparing it. This is the comparator. That's how it is. It's basically a comparison. We are finding some cross signal. Remember, I think that frequency that we measure first. Then we are passing this error signal to some that would how in terms of how generation to generation. And this Because of the opening, that more steam or more water gets boost and some more or some less. If you see anything is going on and you want us to go and how I expect it to write it. One, talk about the sensor, about the frequency sensor and how it measures the converts it to some different or an error signal. That's the first thing. Second thing we talk about that this error signal is fed into understand fed into your transducer, amplify it to the level. Because we're talking about sensors. Sensors they don't produce care about that. Hold on. Yes, got some points that the audio was bad. So if it's better, let us know. Yes, so secondly, we talk about the transducer, how the transducer amplifies that faint error signal that is received. Because most sensors operate up to 5 volts, if with our 8 volts. Want to be able to control the gate with this. So you need a high voltage. That is and that's what the transducer is there to high voltage, amplify the error signal. Then this will be an accuracy command. The accuracy command, what it's trying to do is to show the opening of the gate. So if your frequency is too larger, you want it to come down, then you turn out to the valve or gate that it should just a little or it should turn up a little. You want. The thing you will talk about the inputs to the gate. This accuracy now is full inclusive. We talk about steam or water. That's what it's talk about. That this thing you're controlling the heat, right? You're also controlling the turbine, which controls heater. So you that's what this is the system that's able to control your maintains around 50 hertz or minus 0 system. Next question. Hey, please, we've not gotten any feedback about the sound. Let us know if better. So number two, state any four aims of power system and honestly it's just one. It's so- But yeah, you have four things. Even from PSA, first of all, you're talking about active power. You're talking about this affected DC voltage. So these are the four of a power system. But how do you do? um, First of all, you want to be able to maintain active power balance, that your demand doesn't ever exceed your supply. That's a dangerous situation which you don't want. Business and matter. You want to be able to maintain active power balance. That means that matching demand with supply at all times. That is one of the aims. That you want to be able to maintain reactive power balance. If this also goes into this goes to what it means is that your voltage will become very bad, that reduce, or it will start going up. You know, what is whether your demand is exceeding or reducing. You want to be able to maintain active power balance. Then you want to also be able to control frequency. Control of frequency is one of the key power systems. Yes, and we're getting some reports that it's buffering. We are checking up on that. That's why we are trying to get this. Okay. So we also want to control the voltage profile. Maintenance here, very simple. You don't have to. You see, there are other things we can talk about. We can talk about maintenance of optimum generating. What that means is that you want to generate with the least cost and get the most profit. And so which ones need to come on at that time? Which generators will be on at which time? That in the end use least time. So if hydro, because fuel is more expensive than water. So if all conditions are fine, there's no that is going out of balance. You want to be able to stage those hydro plants rather than the 10. And we move on to the third question. Okay, so we've gotten to this side. Question three: explain the relevance of fish and shunt condensations power system. Right. So if you remember, so see some of the questions they rely on information you don't actually know yet. You see it more in the reactive. Yeah, you see more in the yes. So let's talk about this. Right. Question three. One. You want to it's just two. You want to enhance voltage profile to reduce costs. Right? Your reduction in cost is done in three ways. If you want to explain further, it's done in reduction of losses, reduction of drops, reduction of flows. And all these three will reduce cost. So series and shunt compensation system they are useful because they enhance the voltage profile and they reduce cost. Very very simple. How they reduce cost is reduce the losses and then also reduce drops and finally reduce the boost. Understand? So reduce or minimize costs. Okay, I feel like it's getting better. What is the natural question? Generators rated 150 megawatts and 750 megawatts are buying a 50 hertz finite system. Finite system very important. The system load increases by 180 megawatts, resulting in a drop in frequency to 45.85 hertz. The two generators should increase their turbine powers in proportion to the rating, determining their respective generations machines to accommodate the. So some important considerations before we actually get for a finite system. So your reference power is equal to zero. Now we learn from the question that Hope you guys see what is what is happening that you have a finite system and then you have two generators, one being equal to 150 megawatts, E2 equal to 70 megawatts. And then you're changing frequency hertz for n system. There's 49 point, which is your new frequency, 1.5. You have some couple of machines now. Now the question is that the pace of machines would increase because brought some load into the system. So 180 megawatts into the system. So what is happening? Now, there's an increase of 180 megawatts, so they have their gain. And but then because they're not the same meeting, they will not just share it divided by two and then just move. It doesn't happen like that. Because their ratings are different. One has a larger capacity. So for a finite system, of because your P1, understand, your P1 is 150 megawatts, 750 megawatts, 350 megawatts. And so doing this would give you 0 point. Understand? Can state that because can state in P, like, come back to this right in P. Now you both know that like for the change in like how much each of them would like how much the things would increase. Add them up equal to the new demand that is 180 watts. Meaning that generator one would have to increase like how like it's power by some amount and generator two would have to increase power output by some amount. Add these in 180. 180 is the demand on the system. Assuming like very, very low keys considering it as well. You have these two, there's these two. This is what using we'll be using for our calculation. So solve equation one. What we just wrote simultaneously. Have change in P mech one equal to 10 megawatts. The change in P mech two equal to 150 megawatts. Well, right. In that generator one must pick up its operation by 30 megawatts, and then generator two must pick up it by 150 megawatts. Accommodate the load increase. Now there comes actually solve the question. Now, before actually solve the part, the emissions of the two machines. And we're looking at the regulation constant. The regulation constant for unit one or one. So this is the formula that you can. I know a lot of formulas in this. The formula that you can keep. So Rx regulation for whatever unit is equal to unit in frequency all over inch in alpha unit. We already calculated the difference in 0.15. Yes, so you're changing F you comes your new frequency, right? F4 F2 minus F1 9.5 minus X. So it gives you negative 0.1 instead of the normal 0.5. get negative 0.15 hertz all over. So change in mechanical power hours is one is a megawatt. It comes to regulation content. If I would consider how to best to unit, that is like about same formula Rx negative all over. Right now you're getting to unit two. Relation for if you notice that the change in frequency understand like that change negative all over one megawatt. Now you get 0 megawatts. The beautiful property with this that the self-checking system equals to find the per unit of uh, regulations would be the same. Understand? Now let's get into it. Let's do it for one. I'll just do it for one and check it by doing, uh, doing the other one. Now per unit Rx equal to Rx meg all over. What does this mean? I think that in per unit, the regulation for unit equal to actual regulation times the mechanical power of all over your frequency. Regulation for unit 2 was 0.001 watts. You multiply by your peg 2. That is 150 kilowatts. That's the change. For meg 2 is 50 kilowatts. Kilowatts, I'm right. That was divided by 10. Right now, these are no changes. Very well, these are no changes. It's sort of like a baseline that you're comparing. Your F becomes X 0.015. To calculate, we do the same one, the first one. Get the same 0.015 minutes. Wait and check your answer. Yes. Question 5. Using don't deduce the appropriate equations how the transmission line can be the losses in the line can be reduced. Now there's an important thing that we need to ask first. Equation to understand. Now transmission capacity of the line, you have the maximum transmission capacity known as the static limit, the thermal limit of that particular line. That's the maximum. And this is the formula for that. Magnitude S, it has become better now. Magnitude of 1 by the magnitude of all over reactance. And increase the line, like mathematically, you want to increase the value of something, right? You have, let's say, you want to increase the value of do it in 2 weeks. Increase it I just the yeah, also reduce or your A also increase. So we have 2 ways because of the proportionality, right? So the proportionality. If B increases, will increase. Is also proportional. Now I come to apply the same idea, right? One, and line the capacity of the line transmission voltage. This one you can infer from the line. If the understanding of this is that if one value and V2 of some value, then your transmission capacity of the line will just go up. That's simple. And the problem is that you can't just increase just like that. You can't just say that, oh, right now because I want to send that power, I just want to carry it from one. It's not feasible in the practical sense. Even though this is an appropriate, and then you should write yes. You are writing yourself the question comes from English, but a lot of calculation goes into the transmission voltage. I just don't think the reactance do this is the line reactance. Do this in the okay. When we're talking about the reactance, mentioned that the relevance of reactance is one, improve your voltage, and two, help minimize cost by minimizing your losses, your costs. Um, I was confirming if the sound is a little better because what can we do to the line reactance? So we can install that parallel line, that parallel line. Now, this has this has two benefits. Have lines. So how to think about this is that for effective line reactance just goes down. You're assuming that the voltage, so that's what they also some bump in the voltage. I just assuming that. So if you have two lines now, for effective reactance will go down. One of the properties of parallel heating that the realization of it always gives a lesser value. So one thing we can do under parallel line, two very expensive a line. For example, you have go to the line to refuse it. Although it is that. What we can do is conductor bundling. I just place multiple conductors in or or however. This is also very effective because they'll always move to the form of complete. If you add a capacitive or because you're looking at a line reactance, the line reactance is apart from either normal reactance is always has a negative uses the reactance. So if you add a capacitive into your use your overall reactance. This is what you don't have to like use the existing infrastructure. Yeah, it can help with it. That's what an overall overall reactance that we study in system. So how can losses in a line we're still using the loss. The reason why I'm stating it is that I just want to stay out of trouble as much as possible. But I try not to avoid below the now this is the same equation we're talking about. Now, what we can do mathematically reduce this step. So one significant way of minimizing your losses is also sort of discussed at the time. So you could do uh, uh, now, we're talking about minimizing the line flow. Another one, that's what's like. And you can minimize flow by distributed generation. What that means is that instead of bring all your power, you see, this also has an issue. You can't get it just anywhere like that, right? You have to have dams If you need power in a car can't just get up and say that, oh, just want to reduce the amount of that power has to travel. You want to build a dam in a car. That's it. Don't do that. So what you can do is to you can set up smaller plants along the line so that you don't have to carry bread towards all the way from Akosombo where like Tema. Right? You can supply some towards the high more the other places. Have power, those things. You don't have to supply everything. This is the amount of distance that has to travel. Then also your supply loss. What we can do to minimize so this is one way. And minimize the losses in the line by minimizing line flow. Then under minimizing line flows, minimize low generation. One is minimize those local compensation. Same thing here. You don't want to supply all your 200 bar from just supply 100 where you are. You install a capacitor bank or something. Hide that the power that you need. What is trapped on the line is actually less. This help you minimize line flows. And do by increasing voltage. That's also a possibility. How we can increase transmission? Usual way, just jack it up. That you don't want to run at 160 anymore. You want to run at 2. Then with doing this, your the losses in the line will decrease. Third way we can do it line resistance. This is done through conduction or bigger conductor sizes, and this is also very difficult because of the huge cost overhead that comes with it. Expensive, very expensive. So we try not to do this option to reduce line reactance resistance. Have minimizing line flows, then under this you minimize fuel with local compensation. This voltage to reduce line resistance that you can. Finally, the burnout effect. Okay. Now, just going to state it as possible. Burnout effect going on permanent or intentional or unintentional slight drop or reduction in voltage. So, unintentional intentional drop, very slight. That's why you just don't want to take it. But remind that you still need the 232, but then it can still work at 2 8 5 somewhere 230. Work fine without any, but it has a massive benefit at the end. Burnout effect, whereby there's a phenomenon where one intention very slight when you have voltage that is reduced. And the intention of this, that's the last part of the reduce our demand in the generation system. What this results in is illumination. Usually that's where you see it. That's the four things that you can keep it. Don't keep it. Phenomenon where intentional or unintentional slight drop the intention of reducing power demand from the way of managing your power system demand, the voltage, that will have a massive. So your the effect is two times, right? Reaching end. That's the brownhouse effect. We're done with height. Go to the next. This thing is theory, right? A 110 the transmission line between points A and B, a reactance of 25 hours of power. In the reactive line fluid voltage profiles. When V, now what happens is that you have to first find reactive line flows. And the reactive line flows are two. One is equal to the same just just and you move the L changes. That's what's happening. Now to be able to but as you see, you have V1, which is have V2, you have to find the angle, that load reactance. Remember the question, the reactance said that right? So, we have to find the load or power angle found by valve one. Let's move. It's 2 megawatts. Have 110 over 20 of this. Do the calculation. Right? Please. So now we have our load angle. We just please. I don't know. Should we okay? You write it down and then 4%. 110 volts over 20 divided by 1922. If you solve the second one to procedure, leaving it for the same reactive line fluid. Now we come to question two. Nothing really is nothing A is equal to 1.5 or 1.5. Have to find delta the calculation. Go to see have one being have V1 being 115. I'll be careful here because 1.5 minus U42. In procedure, I just announced get any answer. Third question. In 110, 115, 115. In oh, let's do it. You get your good angle to 9 point. That's very there. In formula one, 1. Okay. This is how you solve, and we are done with the principle of the fractal formula. So the song, is to explain the principle of the. So now, quantity effects to definition. So let's try. So a phenomenon one. Now number two is that the phenomenon of a voltage rise at a voltage end of a long transition rise. And it's what it's when it happens that is interesting. It happens during light loads or night condition, light load on the because I don't know what you're doing in the night with that laptop. Then what it does is that let me come again. Anti effects is the end of a long the night light load conditions of excess bars is me. I'm asking what during light load or like night conditions capacitive current, load current. And this light load condition. capacity, load, the load. When this happens, the line will operate at the power factor. When the line operates at the end, like this thing, it is from this particular side, so it makes sense. Shunt capacity, during light load, the shunt capacity is variable. When this happens, your system will operate at power factor, the running side, because of the power. Like okay, okay, makes sense, makes sense. So the line operates at the leading power. Voltage variations will arise. Variation means that drops or rises arise from the current capacity reactance. Really, really hope it makes sense. Please listen. So voltage variations will rise current, the capacity reactance. Capacitive reactance, reactive reactance, and resistance reactance or resistance. Because of this, there will be some losses. Current itself, your losses will either go up or go down. When these drops, because of the way that they add up, drops add up as vectors. Of this, at the end is higher than the end. What happens is that this oh, okay, this is making sense. Come again. During light loads, during night hours, during 4 a.m. time, load current. Because of this, the line of operation. Now, now when this happens, voltage variations is because of or line resistance reactance, active or line resistance. It will arise because since these drops right don't drop, this has to drop and this will add up as vector to add up. Also that the voltage at the load side is that this has something then one of this one has in that this would arise. And this what is known. But then the definition is that the frequency effect whereby the by end of a long during the night or light load condition. If it doesn't challenge you with an right. Now state where Y series and shunt that's very stable. Accident right there. But put this thing, you have type of computer and you have C where I and where. precision or before high voltage. Now the one thing why we use something is used with that thing, you already know that current why we do this current limiting is as protect is this but two lines of one one as bar and the thing is for you already know the opposite. Pilot electronics helps station pass bar. And now it has there's a different what happens is that help your voltage go to high to low what your switch in for and for reactors right? Help you regulate from voltage low voltage. And there's the thing. For high voltage optimization, high voltage and limiting lines to compensation as bars for voltage. So you can just write it as voltage that capacitors help you and we can move on to the because it's the four power. I don't know, there's this course that we did that's that give us like exactly oh, use these kind of equipment to offer or one photos. I don't know how you want to take it because mostly photos, right? Mostly all is use them. They contribute some oh, instead of power factor because it use active power of reactive. So your power factor will come down. That power factor is all AC motors and lagging power factor, which has overall power factor. One is acclamation because of human ESD, because of the need of the how they work more, because of how I speak, which of low power factor. One is which at a very low or right? In Paapa proper or AC mode. The exception of a few comes to outline three methods of okay, so this question or the question method substitution rather. Outline three methods of okay, senses, business using one using capacity by placing this of all these they do is just control the reactive power of amount of reactive power that you need to put. This question, yeah, we'll come back to this question. Yes, a little bit one that involves you. So the 440 is power supply. Now this one will have to please keep the question by you. A load one for now, they're saying some things. Like they're saying that preloaded power, preloaded power factor of 2.8 again. So okay, let's combine everything. Preloaded power. Now you talk about the power demanded or the power supply needed output by your efficiency. And your output, just as I said that we should just find the output, this output could have been was powered by. So if you check online right now, what is the 5.5? So much, so many places. Try to stick to one and note that this 1 horsepower is equal. You also compare. Try and use this now. Just 50, right? Just write it as you use the rate of 1 because I'm going to check with Google and then tell you what you can. Right now, you see, because it's fully loaded, we don't touch it. But if fully loaded means that it's using 100%. If they said that, come, we'll see it soon, that you are all loaded, is that the output won't be times one per four. That's a ratio that give it 291.2, but right, the load that you have to that. get you there. Now, if you remember from applied course, what is equal to V I do some change of I is equal, then we just go back course. I have this there. We'll be using this now. You already know what P is, right? See that see that they gave you everything, so you calculated your power demanded. Power demanded was 219 watts all over. That is the power factor. What was the power factor? Is equal again. You have some Q that you don't know. So what you're trying to find how much reactive power we need. If you look at the question, it says that PAR that you need. It, that is equal, that is equal to you can do the calculation by yourself. So then while I phone, please confirm wherever you are. I being like 0.526. No, when you do this calculation, give a distance. When I'll be able to find one, I'm going to do the same total load 2 now, half over 4 loaded modules to affect your output. Power demanded, power input, equal to output all over your efficiency. Your output means your horsepower loaded. Let 3 over 4. And you have power being 80 horsepower. Then for all over Okay, so let's get back to it. Efficiency of 90%. Have an efficiency of 90, which gives of 111.55 kilo. We're using the same P on and R. We can make this very sizes. Thank you. Who are P as 111 point watts time. Pi is also less of 2 point. And this you are continuing with now. Now load is a resistive. You know that resistive reactive elements to like it doesn't demand any reactive. Very very clear. And that will be 2 watts. 2 watts, yes. It doesn't demand Q. That is, and we can move on now. Let's look at uh, NOS. Now, it's 95 efficient. This with oversetter doesn't do anything. Although it's installed to drive an additional 100 to need. What's the power demanded by this? Power demanded is in of for your output or to your 8 watts. Only that don't mention it, that means that it's still loaded when efficient to or this power that is to do with me. And we can actually start looking at the question. We've done so many things. I was asking that what is the PA rating? Not the leading. The leading is not actually adding or or asking you what's your PA rating? What's the amount of reactive power to correct your overall system? Now, have, have an overall alpha angle that you have. What we have to find. Angle must be best for. Think about it. We are bringing back our formulas again that we can use so that for overall equation. So we are considering overall system. We want to calculate the amount of that we will need. F5 is 895. That to get after 95, A P, because you're considering the overall system, must be overall. Like, now we'll go back. Motor 1 give us power of kilowatt rating of 19 as then motor gave us 1 watts. As resistive load gave us 200 kilo, 195. All us give us some value. And have 6 of 18 the Q that rating of. Now, the understanding of this is that you have a total power and you have reactive power. Get power factor. Now you have to look at much much reactive power. That total should be equal to existing power as those motors are those motors. Now existing Q, we had some. First one was 5 point, one was 4 point, was 0 for a reactive, most motors just Q. We have it to end. This calculation that was go up 9 9. Makes sense. Now the question is asking that what is the rating resistance, right? Correct. Get your power factor of 0 point. On the angle, use this equation. What Q get get what's the total reactive power that we need? Know that already some of the machines set them up in how. What do you mean that? The remainder is that that means that the remainder must go to the machine that have the AR of 10 give up gets a finally rating. And this is all from apply. Asking you rating, give power factor of give you rating go to or your power is we're talking about the motor right now. 95, 79 point. This is your apparent power. Asking you power factor bonus motor. Power factor from power. The power factor is that's your apparent power, sorry. Power is 79. And with this, is that there's a need for active process type of the motor. Put two bus system reactance 2.25 ohms is yeah, the ohms per unit. The buses has first generate bus system. Here's the active load. The two buses are maintained at voltage 2.98. Load demands at the see the power angle, reactive load 1 Q, reactive generation. So look at this. Let's take a different. Also, I had that's some so let's look at it. Power angle is the system. Now, one we already know V1 is that one to solve. So this particular, there's another I refer to something else. The business doesn't look on. Probably we'll get to this particular one. But let me just run. Now, supposed to get generated here. This is what they give us. This this thing uh, load on the line. The power like that is flowing on the line. You do it and you get 1.1 point good angle. Basically, what they're doing is that they give you and 1 point good angle. Good angle. I'm sure we'll go with it properly. Okay, to get Q1, team says that know the five, this five, delta at will use reactive. Say the reactive generation, all the angle. Just do your function next time. That's the question. Yeah, much more. And if you notice, they're doing something, please understand. You can talk. And doing excellent. In 1.3 view views. Thank you so much for that. And we also want to say something. Hashtag Paapa. If I had, hey, yeah, like that. If I had a picture, I'd have shown the picture next time. As for the new tablet, we have a tablet that thing and then just like have them be lovely like pause.